Hello everyone, today we are revising week 9 contents of mathematics 1 course, which is mathematics for data science 1. Okay, so let's start. So this week starts with the concept of critical points. Okay, critical point, and through critical point it takes you to the journey of maxima, minima. Okay, and then this course starts integral calculus. Okay, it builds for integral calculus. This course tries to build up a better foundation using area concepts. Okay, and for area concept they use normal areas, which is using the formula. Okay, and then they use the Riemann sum, right? And after this they start in the core integration concepts. Okay, so we'll follow this, but we'll see this area concept using a different and much better concept, I would say, in terms of understanding the area function concept, and I will just summarize what is the Riemann sum. Okay, so yeah, let's start. Critical points. Critical point. So what is a critical point, right? So a critical point, let's take a graph first. Okay, let's take a graph like this, and let me make a graph. Yeah, so if this graph is of some function fx, then a critical point at a is regarded if, right, if I would say f dash at a is equal to 0, right? That means the derivative of the function at this point, that's a, is 0, or or the function is not differentiable at a. Okay, either the function is not differentiable, though this condition is used very rarely, but the main condition which is used is that the derivative of the function at that point has to be 0. Okay, so let us try to analyze this graph, and in this graph we can say that yes, these 2 points are critical points, but we know, how do we know that? For this I would ask you to revise the concepts of straight line, or I would say that recall this, that a derivative, if fx is a function, is a curve, I would say curve, then f dash of x at x is equal to some a is the slope of tangent, right? Slope of tangent we know. Okay, this we know. So how do we apply this in this graph, right? How do we apply this? So if the slope is 0, it means that the tangent line is parallel to x-axis, right? The tangent line is parallel to x-axis. So we can say that these 2 points a and b in this graph are those points in which if we draw a tangent like this, we would get it, or that would obviously be parallel to the x-axis, right? So this is the core concept behind the point of critical point, right? Yeah, so if the derivative of a function is 0 at some point, right, so at that point we can say if a tangent is drawn, then that tangent would be parallel to x-axis. And why this is significant, right? So if we analyze this again, we can see that a critical point is an end of an increasing graph, and it's starting the decrease of a graph, right, at this point. Or we can say that at point B, it is the end of the decreasing of graph, and it's the initiation of the upliftment, or you can say of the increasing of a graph. So critical points is again a very crucial concept if we deal the increasing and decreasing graph. But in this week you are taught maxima and minima, right? So let's start maxima and minima. Okay, and we would try to analyze that how the concept of critical points is used in this topic. Okay, so let's try to again analyze this graph, okay, which we have drawn. So this graph gives a better understanding. So a maxima, as the name suggests, it is dealing with something that is maximum, right? And minima, it resembles the word minimum, so it deals with something which is minimum, right? So the first concept which arises is the uh, local maxima or minima, right? Local maxima or minima. So what are these things? So we know that local means which is our neighborhood, right? So in the graph we try to find which how many points are giving a bump like situation, a crest, we would say, in a wave, if you recall, if how many of them are giving a situation like this or like this. Okay, so at all points, if we say, then it's called as local maxima and minima. If you are given some interval, okay, and you have to find which at what point the value is maximum, right? So that thing is known as global maxima and minima, or which is the minimum, right? Respectively, you I think you would understand maxima or minima, right? So these are not very different, but yes, local means you have to tell all those points which are having some curves like this and this, or which are having in their local or in their neighborhood the maximum value. So if we talk about point A, in this point, like in this area, in the line which I have drawn, A is having the maximum value, right? Because all these points are having some low value, but at this point we can say the A, at point A, the value is maximum. And if we talk about this region, okay, then B is having what? The minimum value, right? So these 2 points are local maxima and minima. If we talk about uh, the graph as a whole, but if we are given a graph like this, right? If we are given a graph like this, and we are asked to tell something about the local maxima and minima of this graph, right? So what we can say, and we are also given an interval, right? Like if this point is some A and again this point is some B, right? So if we are asked that find the global maxima and minima, which means that at which point the value of this graph is highest, and that point will be known as global maxima. And at what point the value of this graph, the value of the function, we can say, is minimum, and that point would be known as global minima, right? So this was the concept part. So let's again try to understand. Let's dive into the mathematical part. Okay, what's the mathematics for this? So there are actually a test known as second derivative test, okay, which is very common and very useful while this for before that, I would also request you to ponder upon this point, which is a saddle point. Okay, what is a saddle point? This neither minima, neither I would say maxima nor minima. Okay, that means the situation is quite confusing what to say. The point is neither maxima or neither minima, right? So if we talk about the graph of x cube, it goes something like this. Oh, I have made it so uh, uh, okay, no problem. But if fx is equal to x cube, then at x is equal to 0, it's a saddle point, right? Because at that point we can't conclude whether it is a maxima or minima. So that's that point is known as a saddle point, and that is a critical point. Again, I would say it's not that it's like it's any point, because at any point we can't just say, right, that it's not maxima or minima. But the main point behind this is it has to be a critical point, and we are not able to decide what type of point it is, then that point is regarded as saddle point, right? So let's move forward. And so we were talking about some test. Okay, so yeah, mathematical part of maximum minima, right? So let's start. So as we know that the first derivative, like let us take some assumption first. Let f is a function. Okay, f is a function which is differentiable, which is differentiable. Okay, not at the endpoints, of course, because that's an obvious point, but which is obvious without loss of any generality that anything is happening weird. Okay, so yeah, f is a function which is differentiable. F dash of x would tell, or f dash x tells the monotonicity, right? Monotonicity. How is the graph moving, right? So if f dash x is something, like in this graph, let us say, let's make it again. So if there is a graph like this, so at at if these points are critical points, then uh, at this point we would say that tangent would go like this and the tangent would be positive. So if f dash x is positive, that means the graph is increasing at that interval, and at this point we can say that the tangent goes something like this, and it becomes an obtuse angle, which and tangent of that would be negative. So we say if f dash x is negative, then we can say that it is decreasing, and that interval graph is decreasing. Okay, but if we talk about this point, that what does f double dash x tells, this tells about the maxima and minima of that point, right? So if f double dash of a, okay, that means second derivative of f at point a is greater than 0, we conclude that point a, the function, or I would say point a is minima. Okay, and if f double dash of a is less than 0, then we would say the point a is maxima. And if f double dash of a is equal to 0, then the result is inconclusive. Okay, the result is inconclusive. That means we can't say anything about that point, right? And you know what that point is. So yeah, so this is the mathematical part. So let us just try to apply this concept in one question, right? So let us have that question like this. Question says that find the maxima and minima of fx is equal to x cube minus 12x, right? First thing is to differentiate, right? The first thing to do is to differentiate. That means to find the f dash of x, the f prime of x, which is nothing but, by the simple rule or rules of differentiation, 3x squared minus 12. Next thing is to find the critical points. And how to find those critical points? We need those critical points to be 0. So we equate this f dash x to equal with 0, right? We want that, so we apply or equate it with 0, and we would get this 3x square minus 12 is equal to 0, right? So 3x square is equal to 12, x square is equal to 4, and then x is equal to plus minus 2, right? So we are having two values of x, that means we are having two critical points where the graph is kind of changing its behavior, okay, where the tangent are parallel to x-axis, we would say, okay. So now the next thing is the second derivative test. Next thing comes is the second derivative test. Now how to use this? Now we have found that f dash x is what, 3x square minus 12, right? We again differentiate this and we get 6x, right? 6x. Now if x is equal to 2, f double dash of 2 is 6 into 2, which is equal to 12. This implies f double dash of 2 is what, greater than 0, which means x is equal to 2 is minima. Clear? And if x is equal to minus 2, f double dash of minus 2 is equal to 6 into minus 2, it is minus 12. This implies f double dash of minus 2 is what, less than 0, which again implies that x is equal to minus 2 is x is equal to minus 2 is a maximum, right? So all these things constitute the concept of maxima and minima. Okay, so now let's dive into the concepts of integral calculus. Okay, I think all these things are clear, so let's move ahead, because these things are quite easy and quite understandable. Okay, now the main and I would say non-trivial part of calculus, which is integral calculus, right? Yeah, so integral calculus is not that, I would say, hard, but let's try to understand it, right? So main thing is that area. We know that if the figure is a square, then we can find a square, then its area is a square, and a is what, the side of the square. If it's a rectangle, then it's what, length into breadth. If it's a triangle, then it's simply half into base into height. If it's a parallelogram, it's half, not half, it's just base into height. And if it's a rhombus, it's half into the product of diagonal, that is d1 into d2, and so on, right? So these are, these figures are quite known, and these are, we can say that these are regular kind of figures, right? What if we are asked to find the area in between this graph, like this? And the problem is again increased by saying that find the area in between this interval, let us say a and this is b. Find this area. How would you do that? That's the main questions the mathematicians faced, and they tried to solve it using different methodologies, and they came to a conclusion, right, that we would use integral calculus after a lot of research and all, and the foundation of integral calculus was given by Riemann. Okay, Riemann. So that's why we studied Riemann sums. Okay, so now let us not jump directly to the Riemann sum, but let's try to understand a new or a different type of concept, which is area function. So if you are having a graph like this, right, this is a graph, okay, so it's here, it's passing through the origin, right? So it's quite bad, but no problem, we just have to understand, right? So if this line is nothing but fx is equal to x, which is a very common line, right? So how this integral concept arised? So the integral concept, or the definite integral, I would say, if precisely, is nothing but a procedure to find this area function. A function whose in which if we put some value of x, then that function will give us the area of the figure of the graph till that extent, or till that limit. Okay, how it is attained, right? How this thing is attained, and this thing is attained just by, let us look into this graph and try to analyze. So if this point is some general point x, right, what would be the point of the coordinates at this point? This is nothing but x and x, because this is the line of y is equal to x or fx is equal to x. So whatever would be the value of x in the x-axis, the value at y-axis would be the same. So this point would be having the coordinates of x and x, right? So now if we try to compute the area, what we would get? We would get half into base into height. Very nice. Half into base into height. So half is what? Half is there. What is the base? This length of this part is x. X. Very nice. What's the height? Height is again x. So we are having what? Half x square. Now if we are seeing this concept as a function, if we try to analyze this as a function, then we can write it as ax. This is nothing but a function which is giving the area, and which is a function of x. And if we would go, or if we would jump directly to the concepts of integral calculus, we know by integration that this x dx is nothing but x square by 2 plus c. Okay, c is not dealt, but let's leave it, right? It's nothing but x square by 2, and it's the same here. So this, by this you can grasp the concept more easily, that what is an area function and how it is related to the integral calculus. Okay, so all these things would lead you to the concepts of definite integral. So now the question must be arising in your minds, like what if we got a function like this, like the function of sine x? What if we wanted to find the area till this point? It's like pi by 2. So again, the question is very genuine, but the answer would be the same, that if we integrate sine x dx, right, and find the value, then that would be nothing but the area function. If you put the value of x, you get the area. Okay, now when you study this definite integral deeply, then you are able to just find the area between two intervals. Like it would give you this figure, and the concepts of area function will give you the value from 0 to pi by 2. But if you study definite integral, they would give you like from minus pi by 2 to pi by 2, right? Because we have made it like this, right? So this is the main advantage, or main core concept, or core idea behind the concept of definite integral calculus, right? So let us now move ahead and try to quickly revise what was the Riemann sum. So Riemann was a very great mathematician, and he was the first to formalize this, that the area, what would area be if we are having some different and some weird kind of graphs. He just tried to if this is the graph he was having, then, and this till this extent he has to find the area, then he just told us from 0, let us say from this point, right? he just asked us nothing to do or just to make rectangles, right? Rectangles like this, and find the area. Find the area of these rectangles using sum, using this summation, right? Summation is that means it would continually be added, right? So this rectangle, this rectangle, this rectangle, and till up to this. And he tried to find the approx area, right? And if using the limits, he got the exact area with the limit which we are which will be having here after some time, right? So what he said let f be a function, okay, from D to R, okay, where D is nothing but a subset of R, right? A subset of R. Now let D is the domain is nothing but the interval AB, okay, and he said that P is having, I'm just telling you in my own words, right? P is having these points. The first point is a partition of AB, right? That is choice of intermediate points. Intermediate points, right? So the points can be A is equal to x naught. The rightmost limit would be taken as x naught, and then it would increase up to some xn, which is nothing but the leftmost, or sorry, the rightmost. This was the leftmost, or the limit, or the starting of the interval, and this point B would be the ending of interval, right? Okay, second point, a choice, okay, a choice of xi star, which is belonging from xi minus 1 to xi, right? We can take xi star as any point, and it is this point which would result in the in all those things which are called as left sum or right sum or mid sum from the middle value, which our respectable professor has demonstrated in the lecture, right? So it is this point which is xi star, right? Now what? Now the third point says that, or I would say that then we would just define delta xi, which is nothing but xi minus 1, right? So we would try to find the gaps in the interval, right? This is nothing but the gaps in the intermediate points, right? The xi means the gap between point x1 and x0, and it will go on, right? Now the next point, it says that define something called as norm of P, right? Which is nothing but the maximum value of del xi's. So if we have taken equal intervals, right? If we have taken the equal intervals over here, so if this point is A and B, then all these points are x1, x2, and so on, right? So if all these are having equal gaps in them, then the maximum and anything would be the same. So if we won't choose them uniformly, then we have to take this maximum of xi. If we choose them, and generally we choose them to, to just to ease our task, we generally choose them in the uniform gaps. So the maximum of xi would be nothing but the it would be same, right? You take any point. If it is half of gap, then maximum of xi would be half. If it is in 1 units, then it would be 1. Okay, then the Riemann sum, sum is given as sum of all these points P. So P is nothing but a set of all these intermediate points, we would say, is nothing but the summation of fxi star and del xi, and this value of I is from 1 to n. Right. So this fxi is what? Xi was any choice, and this would give us the value if xi star is chosen as this point, or if this point, then we would get this the length of the rectangle actually, and from the del x thing we are having the breadth of that rectangle, and we are just finding the area of the consecutive rectangles, and just finding the approximate area. And when and in the condition when this del p or the norm of p will tend to 0, that means there are infinitely many rectangles, then the area which was extra or which was left out would become 0, and we would get our exact area. So the definite integral is defined as follows: that let f is a function from D to R for some domain D belongs to R. Suppose the interval AB is in the domain. Okay, so domain can be a huge thing, and we are interested in some AB interval for which we need to find the area. Then the definite integral of f from A to B, of f from A to B is defined as limit of what? Of the norm of P tending to 0 Sp, which is equal to limit norm of P tending to 0, and then this again, this thing fxi star del xi, value of I is varying from 1 to n, right? And this thing is denoted by nothing but this weird snake like symbol from A to B, fx dx, right? So this is the core concept, or you can say the actual concept behind the integral. And one more point of importance, or a point to ponder upon, is that integral, this thing would provide you actually the signed area. Okay, signed area. So this is, you can say, a benefit of integral, or sometimes it becomes a drawback. So we won't discuss it much, because signed area, it means that area would be having some sign. Okay, so this is actually the concept of integral calculus. Okay, so now comes the very important, or we can say some properties which are related to integral calculus.